Human Resources and New Technologies and Mission Types, we have Jim Kaufman, number 26.
Yeah, this proposed white paper is advocating a programmatic change to the Mars exploration program. What we want to try and avoid is what happened to the astrophysics program with JWST, where it ate up all the available budget for other type of science missions. And the concern is that MSR could possibly do the same thing here. So we're advocating for a low-cost alternative program to maintain a diverse Mars science program during the MSR era, what we call the MSR era. In our summary, we note that there are a number of potential architectural solutions that have been studied over the years, which we list here. I won't go into them. And we would plan to, in the actual white paper, expand upon these and provide more details. And then in our summary, we've also so far noted or identified 11 separate investigations that span all 4 MEPAG goals that could be conducted by one or more of these architectural solutions that we've listed here. And we hope to expand on that in the actual white paper. We've listed just some of them here, some of them are summarized here. And then there are challenges for doing this, creating this low-cost program. The one is the number of launch opportunities. And we note the existence of the Simplex program, but we also contend there are a lot of constraints associated with it that make it not ideal for going to Mars. There's acceptance of a lot of these novel new ideas, given NASA's risk averseness, and also lack of alternative launch opportunities, possibly using smaller launch vehicles with much smaller payloads. And so what we're advocating for is a SNEX to MIDEX class Mars mission program to balance things out, and that will also be augmented with ROSES funding for a ROSES funded non-instrument technology maturation program to help mature a lot of the technologies associated with these architectural ideas. And so that's it.
Perfect, thank you. John Bass is up next. That's number 27.
All right, thank you. Yeah, my name is John Bass. I'm a postdoc at JPL, and I'm going to talk about the Mars Science Helicopter white paper, which reflects the science side of a project led here at JPL in partnership with Ames and others. And we're really looking at the next step. So fingers crossed, next year the technology demo will demonstrate flight at Mars, and Dragonfly is poised to explore Titan in the 2030s. So we're finding that rotorcraft can enable science that's impossible from orbit and is inaccessible to landers and rovers. And the overarching goal of this paper is to really identify the overlap between the 2 domains shown on this slide, one being rotorcraft-enabled exploration, the other being compelling Mars science. And out of that, we'll develop a few mission concepts. So starting with the vehicle capabilities really quick, and starting with range, in Jim Watson's presentation yesterday, he mentioned that if you add up all the Mars rovers, traverse distance in the past would be about 75 kilometers, and the range of this vehicle could eclipse that in a matter of weeks, which is game-changing in terms of coverage. We also have access to extreme terrain, like cliffs, skylights, dune fields. There's access to the atmosphere, which is unique for an aerial vehicle. And our payload capability is up to 5 kilograms, which many instruments could fit under. And as far as the compelling Mars science goes, we look to the community. So the Decadal survey, of course, MEPAG goals, as we've talked about. And we also have a JPL A-team study that we're able to leverage. And so ultimately, we want to look at this overlap and identify a few mission concepts to get people interested. So if this vehicle or the science interests you, please send me an email. I'm seeking co-signers, and I'll also post a link to a Google Doc. Thanks.
Perfect, thank you. Chad Edwards, you're up with number 28.
All right, thank you. The title of our white paper is Emerging Capabilities for Mars Exploration. And our objective here is to provide an overview of a broad range of critical capabilities that will be needed to enable the next decade of Mars exploration and beyond. We'll be looking at developments in a number of capability areas. I mentioned a few here: entry, descent, and landing, where I think we'll be looking at trends in abilities to land higher mass to the surface, to reduce landing dispersions, to look at concepts that might allow lower cost access to the surface. We'll be looking at both surface and aerial mobilities technologies, in particular with an eye towards being able to access extreme terrains that have been outside the reach of current rover technology. Very importantly, we'll be looking at how do we open up access to the subsurface, both via remote sensing and actual drilling and sampling techniques as a function of depth. We'll be looking at autonomy and avionics technologies that will enable much more productive investigations on the surface of the planet, as well as looking at communications and navigation capabilities that can increase the amount of information we bring back from Mars, as well as provide infrastructure that can enable very low-cost missions. We'll be looking at power and propulsion technologies needed for future missions, and a wide range of technologies that are enabling the kind of small sat missions you've heard about just a few talks ago from Jim. In each of these areas, we'll be trying to characterize the current state of the art based on our operational Mars orbiters, landers, and rovers. We'll be flagging current technology developments that are on a path to infusion. An example there would be, for instance, the Mars Ascent Vehicle propulsion technologies. And then most importantly, we'll be aiming to identify key capability gaps that are remaining that are going to be required for the next generation of Mars exploration and what investments we need. So please let me know if you'd like to join our effort. Thanks a lot.
All right, thank you. Nathan Barba is up next, number 29.
Okay. Hi, everyone. I'm Nathan Barba, and today our title for our white paper is High Science Value Return of Small Spacecraft at Mars. Low-cost missions could enable and support Decadal-class science by augmenting conventional large missions. They could establish dedicated Mars infrastructure and gather key reconnaissance in preparation for future human exploration of Mars. Small, low-cost missions could play an integral role in being pathfinders and risk-takers for future large-scale missions and encourage collaboration from partners in academia and other institutions around the world. Small spacecraft provide a mechanism for entry of new participants to learn and eventually lead in their own missions for interplanetary exploration. I believe most of us are aware of the low-cost opportunity of small spacecraft, so our paper will focus on the unique science capabilities small sats can enable, such as continuous and simultaneous measurements from multi-element networks for large and small spacecraft in orbit and on the surface of Mars. The implementation section will outlay all the different ways to get to Mars, especially emerging methods like rideshare and utilizing small launch vehicles. This is one key area that enables low-cost mission architectures. Our aim is to close the knowledge gaps associated with implementing small spacecraft architectures to meet Decadal-class science objectives. We will discuss the state-of-the-art technologies from around the globe and focus on key future technology development needs from traditional technologies such as telecom, propulsion, and reliability, but we'll also examine new architectures like low-cost landers that can enable some really amazing science from the surface of Mars at a sub-discovery cost point. The white paper will highlight 3 major applications for small spacecraft at Mars. The applications are science missions, the search for resources like ice and liquid water, and using small spacecraft as a highly capable way to perform an infrastructure role such as telecommunications and reconnaissance, which could further lower the cost of future small and large missions. We will also highlight the lessons learned from previous studies and proposals to get small spacecraft to Mars to help jumpstart new entrants who might want to use similar architectures. Lastly, we will detail the current policy that enables these types of low-cost missions, such as rideshare and cost and risk models. Ultimately, what we want is to highlight how small spacecraft provide tremendous science value because of their low-cost basis and high-value measurement capability. The opportunity for low-cost, frequent access to Mars is optimal and will only become greater in the next decade. Thank you.
All right, thank you, Nathan. Next up is Michelle Minetti, number 30.
Hi there. As you can tell from the many talks that are in this segment of talks, there's lots of impetus behind trying to enable access to Mars for lower, quote unquote, costs and with smaller, quote unquote, spacecraft. And, you know, we spent the last 2.5 decades doing flagship missions, which have enabled Mars sample return to be planned and to enable the Moon to Mars initiative to really be undertaken. But of course, that kind of flagship level investment's also given us dozens of sites on the surface and dozens of science questions that are focused that could be answered at those sites with that kind of surface access. But it's also clear that we're already in a situation where we're struggling to keep long operating successful missions from being ramped down or ended, given the current budget pressures, just the initiation of Mars sample return and the Moon to Mars initiative. So there's lots of science ideas. There's not necessarily a lot of opportunities to go along with that. However, Discovery is a stable, mature opportunity already open to Mars exploration, and it's really a good time to pivot to really developing the technologies and spacecraft needed to access the surface of Mars under the Discovery cost cap. We certainly can do orbiters to Mars under the Discovery cost cap, but we've yet to demonstrate surface access without having pre-existing hardware or a significantly contributed payload. So the white paper overall obviously fits in well with many of the other ideas already presented and to be presented, but it's to push for that investment to make us fit into that Discovery cost box for surface access and for all the science that we are able to do there, given the results over the last 25 years. Thank you.
Perfect, thank you. Okay, the next one is David Blake for his third of the day, number 31.
Okay, thank you. So I'm hoping everything that I'm going to say is pretty obvious. Dozens of geologically diverse and scientifically compelling landing sites were characterized during MSL and Mars 2020 landing site workshops. In order to understand the geology of Mars, its early habitability, potential to support ISRU, human habitation, and so forth, full and comprehensive science investigations are needed at many diverse sites. And the take-home message here in orange, I guess, 20 years of instrument development and miniaturization now allow for flagship-class instruments to be packaged in MER payloads. And I discuss an example of a MER-class payload, which would have a Mastcam, MOLLE, so forth, a robotic arm with a rat, powdering drill, X-ray imaging spectrometer, and an XRD XRF, surprisingly enough, in the body of the rover to provide quantitative mineral analysis. And in principle, solid materials can be completely characterized with just 3 measurements: structure, and by that I mean crystalline structure, composition, elemental content, and morphology. And this payload determines all 3 along with context information. And I know I've been speaking about instruments, but I think it's important to point out that science goals and objectives are abstract and aspirational until observations and measurements are made by instruments. There's where the rubber meets the road. Only by accessing and fully characterizing multiple sites will the full diversity of geologic and morphologic features seen from orbit will we be able to truly understand the early history, habitability potential, and plan for ISRU and human exploration. Thanks.
Great, thank you. And Abigail Freeman is up with number 32.
All right, thanks, Sarita, and I'm glad I get to go where I'm going because I'm going to say a very similar thing to what Michelle and Dave and others have said. And this is sort of a double slide. Half of it is about a white paper effort that's actually being led by Paul Niles. And if you're interested in being involved in the white paper, please contact Paul. And there's a link when the PDF is posted to you can get to a working draft on a Google Forms where the first page is a sign-up sheet. But the argument of our team is similarly that we think Mars exploration is at a point where not all, but many of the pressing scientific questions require measurements on the surface. And these include things like compositional isotopic studies of Martian rock stratigraphies to search for life, to decipher the drivers of changing habitability. We talked a lot about drilling and study of subsurface ice. And then, of course, things like study of active geophysics and near-surface meteorology. And so a big challenge to the Mars program in the next decade and coming decades is our current capabilities of accessing the Martian surface are so expensive. And even making it down to Discovery-class mission, as Michelle had noted, is extremely difficult without pre-existing hardware contributed instruments. So we're thinking about other ways to reduce costs, one of which is kind of hinted at by Dave is the idea about multiple craft builds, which would be beneficial to mitigating programmatic risk and allowing budgetary flexibility. And then also thinking about if we can infuse anything from the commercial sector, taking lessons learned from the CLIPS program and seeing if we could apply that to Mars in a way to kind of revolutionize access to the surface. The second half of this slide is an advertisement for a workshop for the Keck Institute for Space Studies that I'm a co-lead on along with Chris Colbert and Bethany Ellman. That was supposed to be held Memorial Day weekend and was hoping that those results might feed forward to a white paper, but that's been delayed to October. So this is more an advertisement about that workshop. But we're going to have 3 goals. We're going to bring together scientists, engineers, and commercial payload providers. We're going to talk about really what are the most important questions that need distributed assets at the surface, what measurements do we need to make in order to answer those questions, what mission architectures would enable that, and then how could the commercial lunar capabilities be leveraged to help us achieve this goal. And so that is my 1-minute pitch.
Thanks, Abby. All right, we are now pivoting to a planetary mission concept study by Barbara Cohen. I'm trying to keep up with all of the good chats, and we'll, time permitting, visit some of these ideas in the discussion period.
Okay, well, while we're trying to get to my slide, which you'll love because it has a nice cover graphic, I'm Barbara Cohen. I have a planetary mission concept study that was a little bit different from the other ones you've heard, which were looking at a single mission and really trying to figure out how best to implement a mission with very well-defined goals. This mission is called, this study is Geochronology for the Next Decade, and it's really motivated by the fact that NASA has made investments in instruments to conduct in situ geochronology, which is a new capability that we don't currently have, and we are trying to figure out how to best leverage those instruments onto missions in the next decade. But of course, geochronology is something that we want across the whole solar system, if I had my druthers. In this study, we focused our attention on the moon, asteroids, and Mars. And so I'll tell you a little bit about what we're doing. The next slide is our science definition team. We have people that you know and love from the Mars community, also from small bodies and from the moon. There was another study that was submitted called MEPAG, which was looking at a very similar lunar architecture to us. So we invited those folks to join us. So you see a little bit of a bigger science team because we asked those folks to join us and they've been super helpful. Next slide, please. So geochronology, of course, is more than just rock ages. Geochronology is what makes the framework for understanding all the science questions that everyone who has been talking about great white papers has asked. It tells us when those things happen. So when did the outer planets migrate and cause bombardment on the planets? What was that flux? Was there a lot happening at once, or was it spread out over time? That has real implications for things like planetary evolution and habitability. When was Mars warm and wet? How many times have people asked that today? How much time do organisms have to thrive in that environment? How long were planetary heat engines active to cause volcanism and resurfacing? And how long have surfaces been exposed to the space environment? And that has to do with current day Aeolian processes and past Aeolian processes, as well as to astrobiology to see, how far you need to go below the surface to find biosignatures. So all of these questions that we ask about processes on all the planets are really tied together and put into order
and tied to the whole entire solar system, tied to each other by geochronology. Like I said, NASA has been investing in the development of these instruments, and so we want to consider how to infuse those instruments into the next decadal survey on Moon, Mars, and asteroids. Of course, today I'm going to talk to you mostly about Mars. And really the aim was to give the decadal survey panel an alternative, or in addition to if you like, but I really am looking at an alternative to sample return for long-standing geochronology goals in a new frontiers envelope. Next slide, please. I'm not going to show my science traceability matrix. It'll, make your eyes cross. But we have a lot of commonality on each body. We really want to determine the history of major events. We didn't make a science traceability matrix to the extreme detail that you might see in a very focused mission. We're really looking at top-level goals, how to determine the chronology of basin-forming impacts, to look at volcanism in the middle period, 1 to 3 billion years, and constrained history of habitability and hydration. So in order to do this, you need to measure the age of a lithology that you can relate to, probably mostly to crater counting, but if not to a specific geologic terrain. And you need to contextualize that lithology. Many of you have heard my soapbox, which is the instruments, the technical things get us an isotopic ratio, but an age is an interpretation that scientists make. So that interpretation relies on that context and on relating the age to the geologic terrain. So when we talk about mission requirements, of course, we have our whole retinue of mission requirements. The two I'm going to focus on today are the payload, which is there to collect, characterize, and date samples, and about mobility, which is to do this in multiple locations on each body. So we're not talking about taking one payload to the moon and then to Mars, but we are talking about sending one payload to a place like Vesta and getting 2 different terrains. Next slide, please. So the way that this works for the payload is, again, because this is a mission concept study, these instruments should be just generalizable to their requirements. But there are 2 in-situ geochronology packages that have been developed to a state where they will be TRL 6 or higher through MEPAG and DALI investments by the time of the next decadal survey. So those are the ones that we've been focused on because they will be ready to go, ready to infuse into a mission. We picked a spectrometer, an imaging spectrometer that is also the benefit of DALI, which will also be 6 by the time we get to the next decadal survey. And I apologize, I switched those TRLs on trace element geochemistry, which is an ICP-MS, that's an up-and-coming instrument. And then, of course, cameras and sample handling. The cameras and the sample handling that we picked are also going to have the benefit of flying on CLIPS missions to the moon. So we have a good mix of very high heritage stuff and things that are up and coming that are just ready to be infused onto a mission. Next slide, please. So we have the same payload. It's going to go to all destinations. There's very little modification, actually. It's suitable for all destinations. We have to go to the surface. All of these instruments require that we pick up the sample and actually ingest it. We don't have to powder it, so we don't have to drill. You can just pick up a sample off the surface. If you think about like the Adirondack class basalts, there's plenty of little pebbles around on the surface that you can pick up with a scoop and sieve or with Planet Vac, which is what we baselined. Either one will work. Picks up little pebbles, puts them in a triage tray. We pick up those pebbles and we introduce them to those science instruments. So there is sample handling. I won't say that it's simple. It's not simple, but it is much less complex than something like a drill and the Chimera that's on Curiosity. So we are moving pebbles around, but it's engineering. It's not technology development. When we look at our payload, we can analyze one sample in about 24 terrestrial hours. That's with 100% margin. So you can break this down however you want by how long your day is. Obviously, the day on Mars is a lot different from the day on Vesta and the day on the moon, but that doesn't matter. When you have the power, you run the analyses. When you don't have the power, you stand by, and you just keep going until you're done. So a typical layout might look like this, where you're running your samples, you're acquiring them, you're looking at them, you're feeding them to your analysis instruments, and you're doing remote sensing to characterize your site and your samples. You do this 10 times and move to a new site. The reason we picked 10 is a nice round number, but it also comes out of the science. The science requires about 3 to 5 really good ages before you really believe that. Rocks aren't always the most cooperative things in the world, and so we bumped that up by 100% margin. That's how we got to there. If you think that some rocks are not what you're going to want to date, when you pick them up, maybe you want to put an extra margin on that for how many you actually pick up and look at, but don't analyze. This is a little bit site dependent and a little bit body dependent, but this is kind of the order of things. And this doesn't, once you get to this order of things, it doesn't really drive much else. So this kind of doesn't matter for the rest of the mission cost or anything like that. Next slide, please. Okay, so the mobility requirement, I should have put requirement here in quotes. Mobility is something we wanted to explore in this study and to understand how that affects the architecture. Ideally, you'd take the same payload to multiple sites. And on Mars, you might think about something like getting the ancient Noachian crust to say when that formed, if water flowed through that surface to make things like phyllosilicates, when it was a warm and clement environment, not acid environment, when did that happen? So that would be a really great thing to know. You also might want to go to a well-dated lava surface with lots of good craters, where you could say, what was that lava? Where did it come from in the subsurface? What are its trace elements? And then relate its age to the crater counts. So we picked these two sites. They're about 5 kilometers apart. You can see some of our backup sites there, and there's lots of sites that you can think of where you might want to do this kind of analysis. We obviously can't do sample return from everywhere, as much as I would like that. And so these are the kinds of places where you might want to send this payload. And we have lots of places on Mars. We're definitely the beneficiary of many previous missions where they looked at some of these sites in exhaustive detail. So if you're just going to send a lander or a small rover, there's lots of sites to choose from that will fulfill science goals for geochronology. Next slide, please. So we had to make a strategic decision in the study of where to spend our TMEX at Goddard. It's called the Mission Design Lab, where we had to spend our week. We chose to focus that on a lunar case to see if a lunar hopper would work to go to multiple sites, and then see how that architecture extended to Vesta and Mars. Just in the interest of full disclosure, we had a week there. We didn't quite get that to close, but we were close. The thing of it is to hop, people have proposed hoppers in the past. Hopping 10 meters or 100 meters seems to be pretty feasible. Hopping hundreds of kilometers to thousands of kilometers just really runs your fuel up. So what you end up doing is carrying big fuel tanks, and the more you carry, the more you have to launch, and the more you have to launch, the more you have to carry, and you get into this vicious cycle of propellant wet mass. And so you can see just here for comparison, if you could launch 13,000 kilograms of wet mass on a Falcon 9 Heavy, you end up carrying 12,000 of that as propellant. So you get into this sort of crazy cycle. But that's what it would take to hop. Of course, on the moon, you wouldn't want to rove. It takes too far. So the lessons we learned from this study are that it takes a lot of fuel to hop. The moon is pretty marginal for hopping. Hopping definitely works on Vesta, though. So we looked at this just very briefly for Vesta with much less gravity on a much shorter distance between sites. Vesta would be a really great way to hop around with the same geochronology payload. Hopping, of course, isn't going to work on Mars. And so the next slide, I just looked at a
Barbara,
very...
you're past a minute.
Oh, okay, thanks. So I just want to show you the thing here, which is a Mars architecture assessment, and show you what we're looking at. And just go straight to the next slide, which is we really want to have something that is New Frontiers capable mission that's compelling for geochronology. We think we could do that with one lander to one place on Mars. So if you've got ideas on maybe how we could achieve that with advances in EDL and small spacecraft technologies, we'd love to have your input as we refine this kind of architecture assessment for Mars. Thank you.
Perfect. Thank you, Barbara. We're going to switch back over to the white paper topics, the last few, starting with Bruce McKenzie, number 34. And then we'll open for a discussion period. for this session and then move into the discussion period overall. All right, Bruce, go ahead.
Yeah, so hello, I'm Bruce McKenzie. First I want to thank Serena and Johanna for some behind-the-scenes help with all of this stuff. I want to talk about surveying resources for settlement, for permanent settlement. There seems to be a gulf between the geologists and scientists and those architects and others that are advocating permanent settlement. There's just not a lot of communication between, and the advocates for permanent settlement just don't understand why we don't have some needed data and don't understand how hard it is to make these instruments and the rovers and science packages. Anyway, at the Mars Foundation, we've assembled a list of construction materials that might be useful for a permanent settlement. For example, you might want cast basalt or sintered brick or spun basalt. The ingredients for these are pretty much the same, but can we separate the regolith? Can we process the regolith so we separate out different materials to change the melting point or the strength or other properties of the construction material we're making? Or maybe we can find a riverbed or a lake bed that has already separated out sands or clay that might have useful properties. Similarly, even if we know what minerals and chemicals are in the regolith, we need to know their solubility. So could we leach out a desirable chemical or leach out some undesirable materials? We'd like to select a site, preferably from orbit, that has a wide variety of resources. And we are looking for people to interpret the mineral information for construction and refining purposes and fill in gaps and maybe suggest what experiments might be needed. And I am done. Thank you.
Perfect. Thank you. Next up is Sarah D'Souza, number 35.
Hi, thank you, Serena. I'd like to talk to you today about a white paper that we're planning to write that's about non-propulsive control systems for future planetary missions. We imagine here a future where you're returning preserved core samples from Mars, for example, Mars polar regions, for example, or maybe delivering instruments that were once too sensitive for current design entry loads. Essentially, NASA's STMD, Space Technology Mission Directorate, seeks to enable such planetary science missions by funding efforts such as my project, Pterodactyl, to develop these kinds of non-propulsive control technologies for next-generation entry vehicles. And the advantage of these systems include the ability to actually manage sensitive payloads during entry, achieve precision targeting, and also yield mass savings by the use of non-propulsive control systems. Now, non-propulsive control systems typically rely on aerodynamics to actively control the attitude of the vehicle. There are many examples, but the one I will highlight today is aerodynamic control surfaces, which are illustrated in the graphic below. During the course of my project, our team designed non-propulsive aerodynamic control systems for a 1 meter diameter mechanically deployed entry vehicle with a 2U 1 kilogram payload mass allocation that kept our peak G loads low, peak heating rates benign, and resulted in a sub-kilometer miss distance. So there's a lot of good work being done in the area of non-propulsive control systems, and continued investment in these technologies can help advance the state-of-the-art in EDL or future planetary science missions. Our goal today is to seek feedback from the science community and the technology community on what they think the potentials are for these kinds of systems. And we welcome anybody who thinks this might be a good addition to their own white paper or think this would be something that they'd like to see or join us on a white paper. And we're also seeking co-signatories. My email is on the chat and also on this slide, and we welcome all feedback. Thank you.
Thank you. Next up is Robin Beck, number 36.
Good morning, or afternoon, sorry. Basically, this white paper is kind of a pat on the back in that NASA's demonstrated very successfully over the last 20 years or a little bit less, that we know how to get to Mars and successfully. And we've demonstrated the capability to land a metric ton or so of vehicles, with instrumentation. And we expect that same technology, the same technologies that have been demonstrated there, to be equally successful landing Dragonfly on Titan in the 2030s. Thermal protection systems used on the Mars mission so far are sufficiently developed and matured, but that's still assuming that the TPS materials are sustained by industry, and that's another paper, is on sustainability of TPS. But the purpose of this white paper is to encourage further exploration and science on both Mars and Titan, because we have the technologies to support them. But in addition, we look forward to human exploration of Mars, where we're going to have to deliver much, much larger payloads. And so we need to identify the improvements in TPS materials required to facilitate landing those larger payloads. White paper is currently under development, and we would like to encourage collaboration, looking for status on the development of and the current TRL of improved or higher strength failure, scalable to larger sizes, easier processing and manufacturing type TPS materials, such that as we have to make bigger pieces or bigger heat shields, we're going to have to be able to do it a little bit more sleekly and less labor intensive and time intensive if we can. We're also looking for additional reviewers and co-signers for the final paper.
Great, thank you. And to end this with, Shoshana Cole, number 37.
Hi, can you hear me?
Yeah, go ahead.
Great. So this is a bit different from everything else we've heard. This is looking to increase the accessibility of the data that we already have, and also making it similarly accessible for all of the data yet to come. The idea is that a user-focused data catalog will enhance the long-term results of planetary missions. We have the PDS, which is a great central data archive where you know the data will live and it's safe. But in order to make it data actually accessible to everyone, people need to be able to find the data they want and also need to be able to figure out how to use it. So for example, a data catalog would make it easy for people who aren't involved in the mission to find what they want. My pilot study currently is on a Mars exploration rover's data catalog. So for example, say you want to find all of the data that we have on Watchtower Rock. You can type in Watchtower and you should be able to find everything we have on that. Or say you're interested in bed forms. You should be able to type in bed form and be able to see all of the pictures that we have collected that have bed forms in them, so that you don't have to search through many, many, many thousands of images yourself. In addition, a data catalog would preserve the team's corporate knowledge. So why did they pick the rocks they picked? How did they actually do their data analysis? So someone right now can go to the PDS and find a file, but how does one input that file? What kind of code do you need? How did people actually do their work? What were these data collected to be able to do? And if you combine the team's corporate knowledge with easy to find data, you enable contemporary and future non-team researchers to analyze that mission's data. And of course, future researchers might include astronauts standing in Gusev Crater or Meridiani or Gale or Jezero. So when we want to be sure that they can actually analyze the rocks that we analyze, so they need to be able to figure out how to do that from decades in the future. For the pilot project, I have an LPSC abstract and poster, which of course wasn't presented, but you can find it there. And in order to see what people actually would like in such a catalog, we're conducting a survey. So the LTSC poster shows the preliminary results of the survey, but the survey is still out there. Anyone who has any interest in using MER data can click that QR code there or click the URL and take the survey and say what you want to be able to find, and that will help us define what the MER data catalog will have and what we will recommend for catalogs for other missions. Thank you.
Excellent, thank you. And I'm glad you had this in there. I think it's really important to think about not only facilities or methodologies for getting new data, but improved ways for using the data that already exists. This is one of the advantages that Mars has over many of the other solar system bodies. So, okay, excellent. We have 5 minutes more until our scheduled break. There's been a lot of chat. I've been trying to see what needs to come into discussion here. I think most of it's just getting actively discussed in the chat area. John Baps, your helicopter concept has come up a few times. Is there anything that you want to just add very briefly to what the scope of your white paper is? John, are you still there? Okay, well, we see. Oh, sorry, he got off the line. All right, I'm going to let you comment then in the chat if there's anything you need to. The other area is with regards to all of these mission kind of architecture ones. So Jim Kaufman, Chad Edwards, Nathan Barba, Michelle Minetti, David Blake, Abigail Freeman. Do any of you want to add a little bit more to what you were talking about based on all of the discussion in the chat?
I can make this is Chad. I can make a quick comment. There was a question about, sources of investment for these needed technologies. The Mars program itself has a limited amount of funding for technology investments. So I think one of our challenges will be to really understand what are Mars unique technology needs, where the Mars program should be making targeted investments. Where are there more cross-cutting technology needs where we can work with other sponsors like STMD to advance technologies that have general benefit to a wide class of missions, including future Mars missions.
Excellent. And Shoshana, I saw you got a question in there. I think you're somewhat addressing it in the chat, but if you'd like to speak to it.
Which question? Because I was in the middle of typing an answer to one question.
That's the question from Michael I about how your effort kind of compares to existing other efforts for tracking data, and then Meredith made a comment about PDS searches being difficult.
Yep, so the main effort that I'm aware of is the recent addition to the MER Analyst Notebook of being able to search by target, and that should be released in the next couple of weeks, I think. But that doesn't help someone who, say, an Earth geologist who wants to be able to look at the pictures that we have of stratified rocks, for example. The other ones I would love to hear about.
What?
So this is David Blake. I just wanted to, sorry.
Oh, I was just going to say, for Meredith, I also find the PDFs very difficult to search through, and that's part of the inspiration for making a user-friendly data catalog.
Yeah, this is David Blake, and I wanted to say the website that I had on my ChemNX thing, and I put it in the sidebar here, has all the Chemin data. We had the same issue that we wanted to have all of our PDS data and all of our reduced data records and all the raw data available to anyone. So this is all open source, downloadable, including all of our open access papers.
Great.
Excellent. We're actually right at the break time. I'm having some trouble getting my chat window to refresh, but think we're doing all right. I'm going to scan through the chat window for key ideas that were brought up regarding missing topics and such, which will feed into the next discussion. So, Eileen, if you're okay with it, we'll reconvene at 12:25.
12:25 Pacific and 3:25